Good morning. So I hear you had a very intense evening last night, so that's good. So let's continue our discussion on these files and topology and parameters. Hopefully we can wrap this up in the first half of this morning, and then the second half we can talk about membrane proteins. So we were looking at topology files yesterday, so I still have it open. We looked at some of the residues, and as I pointed out, every moiety, every unit is defined as a residue. So let me go up a little bit. Yes, I mean, we talked about aspartate, for example, as a simple example of a negatively charged residue. So now, I hope I had my mouse, but OK. So cysteine, glutamine, so nothing special here to sort of emphasize. Glutamate, another negatively charged residue here. We have the atomic charges, atom names, and atom types defined, as well as bonds and improper angles. OK? So all the connectivity is defined here. Bond angles and dihedral angles will be generated automatically, as you remember. So if you have impropers, then you have to specifically or explicitly define them here in this section. And you don't have to worry about the IC table. It's there just to guess the position of missing atoms. If you have a structure for your ligand, then you don't have to build this part. So you can leave it out. Glycine is special because it has two hydrogens connected to C alpha. When you are doing patching, as we will see, then you have to use something special. And that is specified at the end. Patching, if you are patching this residue as a first residue in your sequence, you have to use a special patch. And then we talked about HSD, different types of histidines that we have to use. So we are going to alias all the histidines in our structure to one of these neutral histidines. HSD and HSE doesn't really make any difference. And then for the special histidines, we go in, look at them one by one, and see whether HSD hydrogen bonding pattern is the best, or HSE, or if you have done the pKa calculation and you have some protonated histidines, then you assign them as HSP. These are the three types of histidines that are available in the topology file. We don't have HIS. We have to be specific about the protonation state and the tautomeric state of the side chain. So let me know if this was not clear. We can discuss it further. This is HSP now. Protonated histidine has protons on both nitrogens and carries a positive charge. So now that I think then we have a bunch of hydrophobic residues. Really nothing special about them. So can skip through, and I would like to just to look at some of the, might be easier to search for it. Okay, so then we get to actually to this very useful section called PRES, which is actually patch residue block, essentially. So this is something common that you have N-ter. So a normal protein has a charged N-terminus and a charged C-terminus, which means that the end, so you have to cap your amino acid with something like that, NH3 plus, for example, on the N-terminus. So you can now argue whether you want to have this default patching for your protein or not, because many proteins actually, that when you download them from the PDB file, you don't have the actual first amino acid or the actual last amino acid. So it's truncated. You don't have the first 20 amino acid. Then you have to decide whether the position that you are looking at, should be protonated or deprotonated. And then there are different ways of thinking about this. Many people leave it as protonated. So you just leave this default behavior. You're going to put this charge, this positive charge, somewhere at residue 20 or 21 in your sequence, which is not normal. So now Sometimes you know that this truncated form of the protein also functions. There are experiments performed on it. So the natural form, you can actually use this N-terminus, this charge N-terminus kind of patch. But in many cases, you might have actually the actual N-terminus of your PDB file too close, for example, to your binding site, to the active site, or something like that. So you don't want to introduce an artificial charge to a place where it doesn't belong, right? So I would usually recommend not using this default patching. So you can actually use other kinds of patching that introduces a sort of neutral, like NCH3, a methylamine, or sort of acetamide, or something like that, that doesn't carry this positive charge to that spot. Yes?
So how do we do that? We have to delete this block?
So then you can actually, you have to change in your PSF gen, you have to use a different patch. You can say first patch it with something else. There are different kinds of patches that we look at. So I can look up the actual syntax, but then you say a different kinds of patch there. So the same applies to the C-terminus. So usually it's left as a charged, sort of neutral, negatively charged COO minus. But again, it's your judgment. So I would recommend not to patch it with these charges. So sometimes you have an arginine, for example, which is already charged, and then you put also this another positive charge to the N-terminus of your protein, which in your PDB file is not the actual first residue of the protein, and then you are going to have two positive charges in that spot. So you have to really take, I mean, sometimes the N-terminus of your protein still is a sort of dangling portion of the protein in the solution, so that's fine. Then you can leave it as charge, doesn't matter. But if it's close to the core of the protein, to the business end of the protein, then you have to probably be careful. In reality, that is in the middle of the peptide sequence, and there is no charge there. So maybe the best is to have a similar representation for that end of the peptide, polypeptide. So okay, so that's actually, but one thing actually that what happens in the patching, or it is in these PRES blocks, what happens is that you do modifications, any kinds of modifications to an already defined residue. That's the idea. For example, so you say, apply this PRES to residue number 21, which is the actual first residue in your peptide sequence. And what's going to happen is going to be things like you can change the atom type for those names. You can introduce new atoms. So like if you have actually just a normal, simple sort of sequence, you have the C alpha, HA, and then you have this N with a hydrogen connected to it, right? So what you're going to do, you're going to delete that simple hydrogen, delete atom, which used to be called HN. And then you're going to introduce three new hydrogens, HT1, HT2, HT3. These are the new hydrogens. These are polar hydrogens. They have different atom types. You are going to modify the atom type for this nitrogen. This is not the same kind of nitrogen. It is an NH3 plus kind of amino group, so you have to change its chemical nature. The parameters will be changed. You are going to modify the charges. You are going to modify also the atom type for Ca to Ct1, and maybe the charge actually in this case is going to be changed. So all modifications here can be done to a residue which is already in your PSF file. Yes?
So you don't delete Ca?
No, Ca is there. Ca is going to be, you don't have to, I think in this case you are only changing the charge, because now it is sitting next to a positively charged. It's going to carry a little bit of the positive charge with it. Why do we need to delete Ca?
Oh, when we deleted Hn, I was deleting a hydrogen.
Yes, so this delete, yes, exactly. The hydrogen connected to the nitrogen, which used to be sitting here, we're going to delete that and introduce three new hydrogens. These are going to be HT1, HT2, HT3.
Right. So could we have said atom Hn, HT, and then switch it to an HC?
So you can't change the atom name. That's the only thing that you cannot do this. If you are going to, so yeah, I think you're going to suggest that we could have renamed Hn to HT1. You can't do that. You can't change the atom name. Everything else you can modify, because atom name is the sort of identifier for this atom, and then all the properties can be changed. Yes?
Does it matter whether we first delete it and then add atoms, or we first add atoms and then...
No, I don't think it matters. Yes, I think it should be fine. So these are things that actually a few of you had really nice applications for the for this command here, so you can take advantage of this. Okay, so we can change we can introduce new atom names. We can delete old atoms. We can change their atom types. We can change their charges. And now we can also introduce new bonds. Bond HT1, because these 3 hydrogens have been introduced, so you have to define their connectivity. And let me scroll down a little bit. I should have. And that way, actually, you modify the kind of residue. So now when you're using this in PSFGen, you say, I don't remember the exact syntax, some command apply this patch to this residue number. Some of the patches are applied to 2 residues because they connect them together. Then you have to specify 2 residue numbers or res IDs in VMD language, as we will see. All right, so now let's move on. So now for glycine, we have a special treatment, as I pointed out, because as you note, it doesn't have one HA. Yes, it has 2 HAs. They're called HA1 and HA2. They have to be treated a little bit differently, but the idea is the same. So for prolines, we have also a special treatment. Proline has a similar situation because it has a sort of a special arrangement, a ring arrangement around the C alpha and the nitrogen, so you have to treat it differently. So now this is now one example of a neutral N-terminal cap that you can use. So you can actually connect this to the nitrogen, a sort of a acetyl group to the nitrogen, and that way you leave it uncharged. So that's what I would recommend to use. Okay, so another kind of patching here for the N-terminus, for proline in this case. So now let's go to C-terminus. We have a similar situation here. So usually that's the default behavior. C-ter, you're going to leave a negative charge, and all the modifications here, the same kind of format. But then you also have a possibility to leave it neutral, which is what I would recommend usually. So what else we have in this patch? So you can actually protonate an aspartate. So that's something, I mean, if you do your pKa calculations and you find out that some of the aspartates have very high pKa, you check their position in the protein and you see, oh yeah, there is another negative charge next to them, or there is a reason to believe that the pKa should be pretty high. It makes sense. You want to protonate that, then you can simply apply this patch to those residues when you're generating the PSF file. So you say, apply this patch ASPP to 21 and apply it to 67. These are the 2 aspartates that have very high pKa in your pKa calculations. And then you leave it like that. The same for glutamate. So you have the patch command to modify the protonation state. You can actually link sort of different images. So you can see this. You can do all sort of, let's call it, post-translational modification that you want to do to your protein. You know, add simple groups, connect them together, phosphorylate it. So it's a very useful way to do these kind of modifications to your protein. Disulfide bound is a sort of very common one that you use. And in this case, you have 2 residues. So you have this number before the atom name, 1. Cb means C beta of the first residue. S gamma of the first residue will be modified, and you have the second residue atom names here. And as you can see, you are going to form a bond between the 2 sulfur atoms of the 2 residues. 1 Sg is going to be connected to 2 Sg, and then you define, oh, by the way, so angles and dihedral angles are automatically generated when you are generating a PSF file, but when you apply the patches, it doesn't generate the angles and dihedral angles. So if you have new angles and dihedral angles introduced because you are introducing this bond, then you have to specifically put them here. So in this case, because you have this bond between the two sulfur atoms, then you're going to have new angles, 2Sg, 1Sg, 1Cb, and you will have new dihedral angles. So you have to introduce them here specifically. Okay, so then you can actually take a look. This is very useful. And we have a lot of patches here. But actually, I think one thing I didn't see in this file, I don't know why, is, for example, water is a residue again. Everything is a residue. Lipid molecules are residues. And so everything that you want, your drug is going to be a new residue because everything was developed for proteins. They're using this sort of terminology that applies to proteins. So that's topology. So now you can see the only thing that you need to tell the program PSFGen to generate the protein structure file or PSF file is to tell it that what residues you have. You really don't need to have the coordinates of the atoms in that residue. You can just specify the sequence. I have alanine, proline, serine in my peptide. It's going to, for each peptide, for each residue, is going to come to the topology file, look for the exact name or an alias that you have specified, and then take the description, the topology of that, and dump it into the PSF file. So now let's look at the PSF file and see. Yes?
What if I have a metal in it? Are there special patches for that?
You have a, what's this?
Metal, for example, zinc or iron?
A metal. A metal is also a residue. So you have. It is there. I don't know actually. For some reason, because I searched for PRES, that's why. So metal ions are also like sodium is a residue, zinc is a residue. Yes, exactly. And you don't have any connectivity, but you need to have the atom type and the charge for that. That's the only information that you have there. So let me then first you in the back. Go ahead. Yes.
For the water molecules, we should turn off the automatic computation of the angles for them, right? For the water molecules.
You should turn off.
The automatic computation.
If it is specifically in the topology file, then you turn it off. When you are generating that segment in PSF language, when you're generating your water segments, then you turn off the auto-generate angle if it's in the definition of the residue.
Yeah, and how do you define this when you want to turn it off?
Okay, so I have to look up the syntax.
Right angle and when you specify the angle, does this automatically turn off?
I have to look up the syntax, but it's a very simple command actually. So you can do it in the topology and you can do it in the PSFGen as well.
From the file then, can I assume that this file holds the topology for the amino acids and the lipids?
So from the file name, yes, exactly. So for example, I mean, usually it goes with sort of these two zeros are my own file naming just to have them on top of the directory. So this is a parameter file for all atom kind of description. It's not a united atom description, which we used to have in CHARM. Version 27 for protein and lipids. For nucleic acid, you have Na, yes. And usually you have the same names for parameter and topology file. They should match each other because then you have the correct atom types there. So let's look at the PSF file just to make it so. Okay, so for topology, again, what you're doing in the, instead of specifying, you can specify the sequence. Or you can say, I'm going to have 5,000 water molecules. Just generate the PSF file for that. Or you can simply use the PDB file for your protein. It's convenient. It has the sequence of your peptide. So that's what you're doing in your actual exercise. But in the PSF file, you're going to get all the information from the topology of your residues and put them here in a way that can be used by the MD engine, NAMD in this case. You had a question also? Sorry, I skipped you.
In the case of metals, is it the same for a metal solution and bound metal proteins? Do you use the same parameters?
Yes, that's the idea. You remember I said, one of the first things I said is that charm or all these classical force fields are based on the idea that you develop parameters for fragments, and then when you put them together, you assume that it's going to work. And unfortunately, although we know that in different environments, these residues behave differently, but we don't have a way of systematically address that yet. But, so now, if you have for some of these parameters are sort of, these are general parameters that we will look at. But if you know that they are not going to work when you put this metal in a protein, or you know for some reason you have done quantum mechanical calculation, you have experimental data suggesting that, oh, the distances should be very different from what you have in the parameter file, then you can go in and modify these. So for the case of ions, of course, there are no bonds. You can define bonds artificially that would keep certain geometry of coordination around your metal ion. But you can also modify the interaction of free ions with the environment. Sodium, potassium, for example, is an example for which people realized that they are interacting with the protein too strongly, and they couldn't get the right properties. So what they did is to modify van der Waals or non-bonded interaction between the ions and the protein. So you can patch these parameters or modify these parameters by adding what is the command? NB fix. It's called non-bonded fix. You can modify by adding extra sort of Lennard-Jones type of terms to your potential. You can make it weaker or stronger or change the properties. Okay, so now in the PSF file, so now what we have in the PSF file. So you start with the number of atoms. So now we have, this is the number of atoms. So for all the residues that you extracted from the topology file, we have 7,051 atoms. So, and then we have the segment name here, the sort of a real index, which is actually used a lot. So you have to be now careful. In the PDB, I told you the indices in PDB are not used by any program. But indices here are very important because we're going to define the topology using these indices. So the first section we're going to have for each atom, we're going to have the index, segment name, then we have a res ID. Within that segment, we cannot have more than one residue with the same res ID, obviously. And then for each residue, we will have the res name. These are the atom names and the atom types. So we are connecting now these two, the charges and the mass. So we have almost everything except coordinates to run our simulation here, right? So now that's the first section. So when you introduce all these atoms, so this goes on and on. And then the second section, so as you might guess, we're going to start with bonds. So these are the water molecules. The res name for water is tip 3 in this case. All right, so then after we introduce every atom with all its properties, atom name, atom type, then we don't have to worry about the names, and we can use the indices here to specify the bonds, the angles, and the dihedral angles. All right. So here, so now the second section of the PSF file includes all the bond definitions. Remember, we have to tell the program what is connected to what. So 5,117 bonds, and these are defined as pairs of indices. 1 is connected to 5, 2 is connected to 1, 3 is connected to 1, 4 is connected to 1. 1 is the nitrogen at the beginning of your protein, and 5 is probably C alpha, and 2, 3, 4 are probably the hydrogens connected to it. So all bonds are kind of defined here as pairs of atoms. So you can simply come here if you want to artificially delete a bond, just delete 2 numbers from here and modify this number here, then you break that bond. Or you can introduce a new bond very simply by just coming to your PSF file and add 2 numbers to it. Right? You can connect, for example, the 2 ends of your protein by an artificial bond by just editing this file. There are other ways of doing it in NAMD, but this is the simplest way of doing it.
So if you add an artificial bond, I guess, between like the N and C terminus, you have to then go in and remove those hydrogens, or
I mean, it depends on you. If it's an artificial bond, just a way to bring the two ends of your protein artificially in your simulation, you want to actually have a very small bond distance for that. You can do it that way. But you don't have to. I mean,
so you can have like 5 things bound.
Absolutely. So there is no way. The program doesn't care. So the only thing the program needs, if you connect 2 atoms, it looks at, okay, these 2 atoms, 1 and 5,000 are connected to each other. So this is CT3 atom type. This is CT3 atom type. Do I have the parameters for that? That's the only thing it needs. You can have 500 bonds connected to a single atom. It doesn't care. Right.
And then where the order of these doesn't matter at all. Right?
The order doesn't matter either. You can have actually probably more pairs in each line also, and you don't have to worry about it. This is a sort of pretty flexible format. So that's your PSF file. So for bonds, you can have a similar thing for angles. So in that case, the only difference is that you need to have 3 indices for each angle, but otherwise that's the same. You can do the same modification. You can define 3 sort of atoms in your protein, maybe changing the angle of helices if you want. You can introduce additional bonds and everything here at the level of PSF. That's the most convenient way of doing it. Just be careful about this index. Sometimes when you are working with NAMD and VMD, they count, excuse me, they start counting from 0. So that could be a little bit tricky. So that's all. Otherwise, this is pretty trivial. So now we are in the bond section. In the angle section, you need to see we have 9 numbers in each line. So we introduce bonds and other bonded parameters here. So I don't think we need to go through them. So now let's look at, as I told you, the NAMD engine, so you don't give the topology to NAMD. So you just give it the PDB file that has the coordinate, the PSF file that has all the information. And now NAMD is going to go to that bond section, for example, and say, okay, these 2 atoms are connected to each other, which means there is a bond between them. What is the atom type for this? What is the atom type for this? And now for each bond, I'm going to need a force constant and equilibrium value. So it's going to go to another file, to the parameter file, to find these 2 numbers that it needs to calculate the energies and forces. So now let's look at the parameter file, which is the sort of last file that we are going to check. So now here we are going to have all the parameters needed for those connections or those bonded interactions, as well as non-bonded interactions in this file. So let's just look at some of the examples. The first section is bonds. So it sort of reminds you of the form of the potential. It's a harmonic potential here. For each bond, we need to have a force constant, Kb, and an equilibrium value, B0. And the units, angstrom, kcal per mole per angstrom squared. And then you have pairs of atom types. Now we are at atom types, no names. These are real chemical sort of atom types. So for each pair, we have a force constant and equilibrium value. So if you want to artificially, for example, change something here, you can make, you notice actually the force constants are pretty high, on the order of hundreds. Bonds are very stiff, sort of degrees of freedom. But you can really modify this section. So when you introduce your own ligand, you might need new atom types here. Then for each new atom type that you're using, then you have to make sure that you have these lines for your drug. So in many cases, as you will see, you can adopt these parameters based on analogy between your molecule and other sort of moieties that are already in the force field. In addition to what we are looking at, CGNFF, which is the charm generalized force field, has a lot of chemical groups in it. So you might be able to find what you need already from CGNFF as far as bonded parameters, atom types are concerned. So check those before you start doing everything from scratch. Okay, so that's the bond section. So then the next section is going to be the angles. Oh, that's the lipid section. The same thing for each angle. We have a force constant equilibrium value. We have 3 atoms forming the 3 atom types forming the angle, force constant. Now we are on the order of tens of kilocalorie per mole, not hundreds, and the equilibrium value. Some I mean, some versions of CHARM used to use the Urey-Bradley term. This is some additional term, so we are not using them anymore. So these are the last two numbers are related to that, so you don't have to worry about them. So this, for bonds and bond angles, the definition of the atom types that form the angle or bond are unique, so you can have only one line per each combination. But for the next section, which is the dihedral angle, things are a little bit different. Okay. I should have brought my mouse. All right. So the dihedral angle, so then again, you have 4 atoms, and then for each dihedral angle, how many parameters do we need for each dihedral term? 3. Good. I'm listening. Oh my goodness. Okay, here. So for each dihedral angle, we have the force constant, we have the phase, and we have the periodicity. So then these are the 3 numbers: force constant, periodicity, and the phase for each combination. 1, 2, 3 numbers here. And the force constants, as you notice, are very small in some cases, really, really small. But then there are 2 things that are different here. First of all, you can have multiple lines for the same kind of dihedral. And that goes back to what we were discussing. One of you was asking about this. So you can have multiple terms that can be added together to give you really different forms of the potential energy surface there. So for example, the example we used yesterday, if you have a cis-trans isomerization, so the first approximation is that cis and trans are both minima, and then they have the same energy. You can introduce this by a cosine function that has a periodicity of 2, right? Something like this. And then, but if you feel now, I mean, the cis should be a little bit more stable and lower in energy compared to trans, then you can introduce another term here for the same combination that has a periodicity of 1, has a minimum at cis, and a maximum at trans, right? And then, but of course, the force constant there should be really, really small because you just want to adjust your potential a little bit. So you can introduce another term with a periodicity of 1 and just adjust that a little bit so your cis is now a little bit lower in. Thank you very much, Mark. Thanks. Perfect. Hopefully that. So you can actually have really complicated combination of these dihedral terms to give you really complicated forms of the potential. So if we get the time, I'm going to. Okay. I'm going to show you an example. So of this, how we use this. Okay. Come on. What did I do? No. Somehow it doesn't. So I'm going to show you an example of this kind. So that's one thing. So you can have multiple terms. If you have multiple terms for other bonded interactions, NAMD is going to stop. If you have multiple terms here, it's not going to stop. So you can easily make a mistake, actually. So be careful about that. Just make sure that you do it slowly and carefully. So this is, for example, one example of what I was talking about. So you can see you have 2 terms. It doesn't make sense to have 2 terms with the same periodicity and phase, because you can do that in one term, but usually you have 2 terms. This is the main term here for this combination. It has a high force constant, 2.75. This is the periodicity. But then on top of that, you can have a little sort of additional term here that modulates that shape of the potential a little bit for you. So that's one thing. The second thing is that for some, you can use wildcards here. So like, for example, if there are so for main kind of interactions, you specifically use them, but then you can have for little hydrogens here and there that you don't want to specify a Explicitly, you can use a wildcard. I'm just looking for an example. So the wildcard is called X here. Yes, here. So we can have terms like this, X, C, C, X. And then if you have a combination in your PSF file for which the program doesn't find the exact match for the atom types forming that dihedral angle, it tries to find something in the wildcard section. So it doesn't duplicate. If you have explicitly, like for example, S, C, C, S, if you have it explicitly, it doesn't use this term. But if you don't have it defined, then it tries to find something in the wildcard section for that. So that's what X means. All right, so that's the parameters. And then after that, so we are done with the bonds, angles, and dihedral angles. And then we have the improper section. The format is pretty similar. You have 4 atoms forming the improper angle, and then you have the force constant and the equilibrium value. This is a harmonic kind of potential that we are using for improper dihedral angles. And there are 2 columns that are ignored here. Note that the second, one column that is ignored, second column of numbers is ignored. That's there for consistency to previous versions, so you don't have to worry about that. And here, as you can see, you can also have wildcards in improper angles. So improper angles are here. And then we go to the non-bonded section. So here there is something important to keep in mind. So you can see there are certain sort of conditions that are used or have been used to test these parameters, and we try to stay close to these conditions. So especially the cutoff distance is important. So again, I mean, we might think that if we increase the cutoff distance, we would be calculating everything more accurately, but the force field has been tested and adjusted using these conditions. So that's something to keep in mind. You can always do it and see what happens, but you have to remember that now you are going beyond the sort of realm of what has been tested extensively and how these parameters have been developed and adjusted. So for van der Waals parameters, we have epsilon and R min values, and we talked about this. You are using the combination or combining rule to generate these parameters for pairs of atoms for ij. So the only thing we need to do here is to specify these parameters for individual atom types. For each atom, again, we have an ignored column here, another ignored column there. So for each atom, we have the epsilon, and then we have the R min value, which is the radius. That's what I was trying to say yesterday. You see, I mean, this is already, in this case, R min divided by 2 is going to be 2. So don't worry about that. It's essentially the radius of the atom for the first one, the radius of the atom for the second one, and then you use the combination rule here to get the R min ij that you need for your potential here. Okay, so that's all you need. So let me see if there is anything else. Oh, these are your metals, for example, sodium, potassium, chloride, calcium, magnesium, and cesium. So the metals are at the end. If you want to introduce another metals, you can do it here. Okay, so these are all the files. So again, let's just go over it. So you get your PDB file, usually for your protein. Then you use the sequence of residues in the PDB file. And then you go for each residue, get the topology information from the topology file, dump them into the PSF. And then for each bonded interaction, you need to have the parameters in the parameter file. So when you want to start your NAMD, you need only the coordinates, the PSF file, and the parameter file. That's all you need. Any questions so far? Okay. So let's now move on a little bit. So see, I mean, you did a little bit of this yesterday. So now the question is, what are the strategies that we use for parameter optimization? You can always start, or you will always start with a set of parameters that you adopt from what you have in the force field. And then the rest, it depends on what you want to do. First of all, before I forget, before you start parameterizing a force, a new molecule, make sure that you check and make sure that nobody else has done this tedious step. So you can check the literature, you can Google it. That's probably more efficient. Or you can actually check the CHARM website. They have something called the stream, where you have a lot of different molecules that are not in the sort of standard biomolecular kind of topology and parameter files. Check those and make sure that nobody has done it. Of course, if somebody has done it, you have to check it and make sure that it makes sense. People make mistakes. So, but actually, it's going to be a very good starting point for you. So you don't have to write the topology file and atom naming and everything. So very carefully, maybe. So minimal optimization is usually by analogy. Again, you look for chemical moieties in the database in the force field that are similar to what you need. And then you adopt the atom types. That's going to be very quick. Gives you a starting point. For many applications, it might be enough. But then in some cases, if you have sensitive cases, if you want to calculate free energies, you need to actually do a little bit more work. So this is called maximal optimization. It's very time consuming. It's very difficult in some cases. And I will give you an example of this kind. But again, that's what it takes if you want to properly develop a force field set of parameters for a new drug or a new ligand. If you do that, sometimes actually you can even publish that as a paper because it's a very time-consuming and tedious step. So you can do that and provide what you have to the rest of the community. And again, choice of this depends on what you want to do. So sometimes you want a quick screening of a database of molecules. Definitely you can't go through the maximal optimization route. But sometimes you want to calculate free energies, very sensitive mechanistic studies, things of that sort, then you have to do maximal optimization. So I've already mentioned that to start, you should check the CHARM website. Alexander McCarroll maintains this website. Here and there you have pairs of topology and parameters, as well as many additional molecules. So that's a good starting point. So about partial charge assignment, I think we discussed this yesterday. Yes, there are differences between force fields. So let me back up, actually. I told you yesterday that actually probably this is the most important thing that you need to do. Again, if you have a ligand, bonded interactions within the ligand are going to matter because they determine the conformation of your ligand. But probably what matters most is how this ligand is interacting with its binding site in the protein and how it affects the protein dynamics. And for that, the strongest interaction that you have is going to be electrostatic interaction, right? So that means that you should probably always spend some time in terms of calculating these charges. So for the bonded part, you can probably find similar bonds, similar atom types from your force field already, from CHARM, from all the files that we talked about. But then at the end, if your molecule is not too complicated, I would suggest that you do a charge calculation. How are we going to do charge calculations in CHARM? So what we are going to do as we, let me see if I have a slide here. Yeah, so maybe actually I show this one here. So what we are going to do is to, for each group, what we do is to place a water. For example, let's say this is your molecule. So, right, this is the molecule that you want to parameterize. So first we look in the database, and then we find, well, I mean, this part looks like tyrosine, right? This is the side chain of tyrosine. This part looks actually like a NMA, or it's very similar to actually ACE patch. So you can nicely adopt the parameters, atom types, and everything, bonded parameters from these patches. And then you have something in the middle that might require actually sort of attention, because you have a nitrogen which is engaged in a peptide bond, but it's connected to an aromatic ring. So that's going to be a new kind of moiety here that needs attention. So what you're going to do is to adopt all those bonded parameters for these guys, but then you need to calculate charges for this moiety, and I would say in this particular case, because this is not very large, we can calculate charges for the whole molecule actually. So how is so let me actually just see one example. So what is going to happen in what we are going to do is for each hydrogen bonding atom in this molecule, we are going to place a water next to it. You can see, for example, for this case of this nitrogen, we can place a water there and optimize the configuration of this molecule with that single water molecule using quantum mechanics. And then we come back to the classical description and try to reproduce the distance and the energy, interaction energy between the water and our molecule by adjusting the charges. I know it's a little bit confusing, so let's simplify this. I was hoping that maybe this would be better. Let's say actually you have a simple case of this model compound that you need to parameterize, and then you use the charges that you calculate for this for your drug, right? This is one of the fragments that is needed. So in CHARM, the idea is you want to reproduce the interaction between water and this chemical group or this molecule, because the charges that you're going to put there, their job is to represent how this molecule interacts with its environment. We have multiple kinds of the environment, but we decided that water is going to be the most representative form of the environment. So we are going to actually form this, build this, and then quantum mechanically calculate the optimized geometry for this guy. And then you see what is this bond distance here and what is the interaction energy. Okay? So you get this from QM. And then you come back to your force field. You also get from your QM calculations actually Mulliken charges. These are going to be your starting points. You get this from QM calculations. It tells you, for example, the charge here should be 0.8, negative, 0.4, positive, etc., right? So now you take these charges, these Mulliken charges, and come back to your classical world. In the classical world, you have a fixed water representation called tip 3 that has fixed charges. So these are fixed. We are not going to change those. But then we try to modify these charges on our model compound in order to reproduce the distance and the interaction energy classically, right? So you get the interaction energy from QM, and then you adjust this. If interaction is too strong, then you have to modify, make these charges smaller probably, so you can get the right interaction and right distance for the hydrogen bond. So you have to do this for every group, every polar group in this case. For example, there has to be a water connecting to this hydroxyl group from here. You can have another one over there, the nitrogen here, the carbonyl group here, etc., etc. So this could be actually, this is probably the most tedious part in charge optimization in CHARM, unfortunately. So other programs, now let me go back here. So in AMBER, as we discussed, they use ESP, or electrostatic potential fitted charges, which is easier to deal with. So in CHARM, the interaction-based optimization could be tricky. We cannot change the water model in CHARM. You can see everything is fitted to tip 3. You should not use a better water model. we are stuck with T3P in this case, and could be very difficult. For example, you can have a case in which a water interacts with two sites in your model compound, and that makes it a little bit complicated to analyze the interaction energies. So I have talked about conformational dependence of the partial charges. If you have different conformations, these charges are going to be affected. That's one of the problems associated with lack of polarization. So we don't have these things. If you are, for example, looking at a methyl group, you might calculate different charges for these three hydrogens in your QM calculation, but you have to symmetrize that before applying them in your classical description, because they are going to rotate freely in your classical MD simulations, right? So when this hydrogen comes here, it should look like this one. It cannot have a different charge, you know, you will have imbalance there. So try to be as consistent with the force field as much as possible. So I have a comment here. Sometimes it's very difficult to follow the standard procedure for developing charges for your molecule. I have seen a lot of papers where people are doing it differently. For example, for charm, they are using ESP charges. If you do that, just in your paper, probably you have to describe that I know charm does it differently, but for technical reasons, for technical difficulties, because we couldn't get convergence, so it was very difficult to follow the standard procedure, we decided to use ESP charges. I know that I'm doing it differently, so people realize that you didn't make a mistake or something. And and it depends on the case. So usually, if your case is very complicated, cannot go through this, then it's acceptable to use different charges. Yes, we try to be consistent within the force field as much as possible, but sometimes it's technically not possible, and as long as you're aware of that and justify that and explain it, you should be fine. And I think we talked about pK calculation. These are important aspects about the charges and electrostatic interactions that we covered already. So now let's go through, this is an overview of a toolkit that we developed in the group. So the main developer is Chris Main, who actually, these are some of the slides that I borrowed from him actually. Because the developing actually force field is very difficult and very tedious, especially for inexperienced people, so we decided to develop a tool that sort of simplifies some of the steps. Still, you need to know what's going on, you know, but in order to go through those steps, this toolkit is going to help you a lot. There are other programs and tools available. So, for example, ParamChem, SwissParam, and Match, they try to find parameters-based knowledge for you from a standard force field. Instead of you looking at the molecule and trying to find the carbon that looks like the carbon that you need in the molecule, you can use this to find those parameters initially. So we have also these three programs. Actually, Paratool is something that we have been developing in the center for a while, but it's not complete yet. But then FFTK is a sort of more mature version of what we have been doing in Paratool. There is something else, GAMP, that does a similar thing. So now the idea again is you start with your drug. Then, as I pointed out, let me repeat this, you can actually adopt some of the parameters from known chemical groups in your force field. You will have some new types that need special attention. For these new types, you need to calculate charges, not only for that, but also for neighboring atoms or groups. And we will have new kinds of bonds here, bond angles, as well as dihedral angles that are introduced when you put together these two known moieties from your force field data. So what it takes, so the program is going to facilitate all the workflow that you have to go through. So you start with a PSF and PDB file, you input that. Then it's going to do charge calculation for you, and then assignment of bonds and angles and dihedral torsions. So this is actually the workflow. So when you start with a new molecule, So the first thing you're going to do is going to optimize the geometry of that molecule and calculate the charges. Okay? So you do this based on this procedure if you are doing charm, if you are doing amber electrostatic potential charges. Then the next step is to calculate force constants for bonds and angles using quantum mechanical calculations. So you do a QM calculation, you get the second derivatives from your QM calculation, and by using the second derivatives, you can get the force constants for bonds and angles. This is going to be a little bit difficult to do the similar thing for dihedrals because there is a lot of coupling between different dihedral angles. You can't really say that this frequency that you get from your second derivative calculation is for dihedral angle 1 or 2 or 3. Sometimes it involves several of them moving at the same time. And that's why for dihedral angle, we're going to do it differently. The way we do it is for each dihedral angle that you want to calculate the parameters for, you are going to rotate it 15 degrees and optimize the rest of the system. And through this, you can calculate the potential energy surface for the rotation of that dihedral angle quantum mechanically. Then you get the numbers for the rotation of dihedral angle 1, do it for the second one, third one, fourth one, and then you fit them to 1 or 2 or more dihedral terms in your force field. Remember those lines in the parameter file with different periodicity and different force constant. So there is a fitting procedure involved there too. So this could be tedious because you have to generate all these input files for your quantum mechanical program, calculate the energies, extract all the information, and then do the fitting. Charges are complicated because you have to place water molecule next to each functional group and then generate the input file, calculate the energies and distances, get them out, and then do the fitting. So this could be really tedious and take months actually. So what we have been trying to do in this toolkit is to really actually automate the workflow. Again, still you need to know what's going on and check the quality of the parameters at the end, but then to a large degree we have simplified all these steps. So yes, I mean, like you have to get the geometry optimization, water interaction energy, and then come back and optimize your charges. The second step, which is for bonds and angles, involve frequency calculation quantum mechanically, and then you have to transfer your Hessian into internal coordinate. And the last step, which is for dihedral angle, you have to have torsion scan for each dihedral angle, and then optimization and fitting it to a set of parameters in your classical description. So let me actually go to the next to give you some idea of how this thing looks like. It gives you actually a set of tabs. It is released with VMD. You can actually use it. A set of tabs and then walking you through the steps. It provides actually very nice visual feedback and sort of interactive window here where you can see all the parameters. You can manually change them. You can reject actually some of the parameters or delete some of them or zero them and ask the program to recalculate this from scratch for you. So you have actually really a sort of transparent way of seeing what is happening also within the program. We have optimization geometry. This part actually generates all the input files that you need for your Gaussian job. Then once the QM calculations are done, it sort of parses all the output files and gets all the numbers that you need. And that is particularly important for water interaction kind of QM calculations that you need. So it really facilitates everything. So I mean, all the people in my group who knew how to develop force field now are using this because it's so easy to use. Yes?
So what if you're sort of starting based on maybe a crystal structure, some ligand, and geometry optimization takes you far away from sort of known structure? Have you had a case like that? How do you deal with it?
I didn't have a case like that, but again, I mean, we need to have an optimized geometry to get the frequencies and everything. So I think we are going, of course, this geometry is going to be affected by the protein environment. We understand that. But you need to be at a minimum structure to go through this process. So I would calculate it using the conformation that I get. I mean, maybe you can recalculate the charges for the conformation that is relevant to your crystal structure, because it might be internally affecting the charges, right?
Has anyone tried to implement like the mobile block testing technique, or one of these newer past several year techniques that let one not truly optimize the sort of a faux optimization?
I see. No, as far as I know, no. Because I mean, here, really, I mean, the problem is that we have to have a set of fixed charges. I mean, except for polarizable model that is coming, here we have to decide. We can go with one conformation, calculate charges for that, and we are stuck with that. So you can actually play with this and let me know what you think, if you have any feedback. So it has also actually a nice interface for seeing the convergence of your fitting procedure, to see if the charges, what part of the sort of fitting procedure is doing most of the job, whether everything is converging or not. So very, very easy to look at this. And that's actually one example. Again, you can see, so it's going to go through your protein, through your molecule, find all the important functional groups, and then place the water there with the right, correct sort of placement, generate the input file for Gaussian. Of course, you have to run the Gaussian job somewhere else. It doesn't run all the QM calculations for you, but it gives you all the input files. Then you run the jobs and bring in the output file. Then it reads the information and it starts doing the fitting. And then actually, it also compares the QM calculation with MM energies, for example, QM energies and MM energies, and then you can see how sort of it is converging. This is for dihedral case. It also generates all the scanning, torsion scanning input files that you need. Then you run the job, give the output back to FFTK. It extracts all the information and plots them for you. And the good thing about this here is that it provides default values for many steps that you need, but it also gives you freedom to change them. If you know what you are doing and you want to modify this, you can actually do it very easily in FFTK. Okay, yes?
Does it only work for Gaussian?
So right now, we only generate input files for Gaussian, and we parse Gaussian input file, but we are trying to extend this to games and other sort of QM. Right now, it only works for charm, but we are also extending it to amber force field. And there, we only have to worry about the charges mostly, because the rest of the parameters are very similar. So that's very, very useful. So now, let me see. OK, I think I'm going to skip some of these. So just to point out that these force fields are constantly being improved. So in many cases, once you run longer simulations, once you apply the force field to different examples, different cases, you realize that there are significant deficiencies. We understand actually classically you cannot describe the behavior of a molecule completely with a bunch of numbers. I mean, you have a water here that is represented by 3 fixed charges. There is no way that this water gives you all the properties for diffusion, dielectric properties, or hydrogen bond interactions based on the 3 fixed charges. You have very dynamic electronic system that cannot be represented fully using these simple descriptions. So you have to know what are the properties that you want to represent and reproduce, and based on that, you might have to modify your force field. So this has been done. So we have had very simple description, for example, for some of the dihedral terms, and then later when people use better model compounds, sort of larger model compound that included more of the molecular system, they realize, well, I mean, things look very, very different from the standard case. So in this case, for example, you see we are looking at a dihedral angle for the central bond with two simple single bonds next to it. Looks like this, classical sort of torsion potential. But then if you have double bonds there, neighboring your single bond, then the potential looks very different. And that results in a very different behavior of lipid tails for unsaturated and saturated cases. So for a long time, for these single bonds in unsaturated tails, we have been using this kind of description. And that resulted in having two rigid kind of tails. Whereas now, since a few years ago, people realized there is a very different potential governing the rotation of these single bonds when double bonds are present. This is not a conjugated system, by the way, just don't get confused. It's not conjugated, but the presence of those double bonds significantly changes the potential energy surface of single bonds in the system. And in this way, for example, this way, these two main sort of minima, some of the minima here are separated by large barriers, whereas in this case, these two guys, in the middle, they are separated by a large barrier, but on the side, they can easily exchange because the barrier is very low. So this gives a much more sort of flexibility to the tail that results in very different dynamics. I'm just going to rush through. You will have these slides. You can check. This is the work done by Scott Feller, a very kind colleague of mine who provided this slide. And you can see there are different dynamics for the saturated case and unsaturated case because of changing these parameters now. So, for example, if you look at the displacement of the last methyl group here, you can see that you have a much larger displacement for the unsaturated case. It moves much more. And that, of course, results in different dynamics and how it interacts with proteins, for example. In the case of unsaturated case, you can see that the lipids are able to get closer to the protein because they are more flexible and they can fit into crevices. So you can interpret that as sort of more attraction between those unsaturated tails and the protein, which of course can also affect the protein dynamics. So this is one example of the fact that as we realize significant or major deficiencies in our force field that can be fixed, we go back always and use better model compounds and improve them. So this is constantly happening. Make sure that you are taking the last version of the force field. For the case of lipids, for example, you have to use charm 36. Now we have 36 actually, which is the best set of force field parameters. Maybe this is not what we are using in the tutorials. Please, some of the parameters that we are using in the configuration file of these tutorials are also pretty old. This is just an example. I mean, we try to update them as much as possible, but sometimes if you change a parameter, now we have to regenerate all the example log files and the analysis and everything. So this is not easy. So just keep that in mind. For example, I don't know if that's something, the damping coefficient, gamma. If it's 5 in your examples, please don't use 5. Use 1 or 0.5 or something small. The damping coefficient dampens the dynamics of each atom in your system. And if you use a very large damping coefficient, then atoms don't move enough. I mean, we already have a problem with time scale. Atoms don't do much in our simulations. And now if you dampen them even strongly, then you don't see anything happening in your simulations. Just keep that in mind. So so one thing that I've talked about is polarizable force field, developed primarily now by one of the main groups that are almost there, the groups of Benoit Roux and Alexander McCarroll. So they have already almost ready force field for proteins and lipids, and hopefully soon we will have this. It's going to be a little bit more expensive, but again, that's going to take care of one of the major deficiencies in our classical description, which is lack of polarization, right? If a sodium ion comes close to your protein side chain, you expect this positive charge to change the electrostatic or electron density of this side chain significantly. But this currently doesn't happen in our description because we have a fixed charge there. So they are trying to address that to some degree. Yes?
Will you still have to calculate like sort of equilibrium charge?
Yeah, I mean, the way there are, I don't know if we talked about this, but yeah, so you have this Drude particle, this additional little particle that carries a small fraction of the mass of your atom. Instead of having a single point in a space for your atom, you're going to say, okay, this whole thing is going to have a big mass m. Now I'm going to have it a little bit smaller, m minus m here, and I'm going to connect a little guy here with a mass of m. So the total mass is not going to change. But then you're going to actually, instead of having a single fixed point charge, you're going to have a little dipole here. You can have a, let's say, a little positive charge here, and you modify the charge, let's say. So that's Q2 and Q1 together will be the same net charge of the whole system, but then this gives you a little dipole. So if this atom moves around in response to the electric field of the environment, if you bring a sodium ion, that little positive charge is going to move to the other end, and that gives you a little bit of representation of the polarization of electrons. So that's the idea. Of course, then it becomes more expensive because then you have to adjust the position of this little Drude particle every time step for each atom. Becomes more expensive. That is the main concern. You know, every time you pay more attention to your enthalpic term, to your energies, then you are more limited in describing your entropy, which is a problem. So there is always a compromise between the two. So I mean, it's not true that every time you have more accurate description of the potential energy function, you will be able to do better simulations, you know, because it might become more expensive, then your sampling is going to be even more limited. It depends on the system, what you want to get out of it. So like coarse grain models, I mean, the description of potential energy function is probably pretty approximate and much worse than what we have in atomistic description, but they give you much longer time scales and sampling and everything. So there are trying to get, there are a couple of other ideas of how to implement polarization in a fast way so we can do things better. But so far, again, based on what I understand, this is now a working one for which we have a new set of force fields actually available. That's another thing you need to realize. When you're developing a force field, you probably don't get a paper for 3-4 years if you're a student. That's going to be a big problem, right? I mean, it's very difficult to get grants because you're not making any discoveries when you're developing a force field. So it's a very difficult thing to do, and not many groups are doing it. So, I mean, these are really good citizens helping the community. It's a long process. They have been doing this for several years now, and we still don't have it available. So you have to test it a lot. You have to go and redo everything from scratch, all the fitting, all the other parameters. So it's a very difficult thing to do. So that's one reason it doesn't happen very often. Okay, so let's have actually other questions. Then we can have a short break, and then we can talk about membranes a little bit. Good. So let's have maybe 10:30 we can reconvene. That gives us 12 minutes.